All right. So here we go, folks. 7.1. So this whole new chapter, okay, so this is going to be the chapter that we have for exam 3. This is not on exam 2. It will be on exam 3, okay? But at this point, what we know is a lot of the identities, okay? Now, for some of you who maybe are like, when did we learn these? These should be in your 5.3 notes, all the identities, okay? So please go back and check your 5.3 notes for those identities, all right? We're not gonna write them out again, but we're gonna use what we already have, okay? Now, what we've learned so far is we've taken a look at some cases where we're simplifying trig expressions using these identities, okay? And now what we're moving into is verifying trig identities with ones that we already know, okay? For better, for worse, this is like one of my favorite things about trig. Okay, there's so many things that we can show are true based off of the limited things that we actually know, right? So what does it mean to verify? So if you think about what it means to verify, all it means is to make sure or demonstrate that something is true or accurate or justified, okay? And so one of the things that we really need to start to do is be a little bit more disciplined in convincing someone that something is true, okay? And we're going to focus on what it looks like to verify identities graphically. So we could kind of look at some pictures. And mostly we're going to focus on what it looks like to verify identities algebraically, okay? All right, so that being said, let me pull up Desmos real quick. Okay. So we're going to start with these two quick examples of what it means to verify trig identities graphically, okay? So the first one, example 1, says cotangent theta equals 1 over tangent theta, okay? And so what we're going to do is we're going to go into Desmos. We don't know what colors Desmos is going to make these graphs, but we're going to graph cotangent as one function. And then separately, we're going to graph 1 over tangent. Okay, so we're going to graph two functions, cotangent and 1 over tangent. Okay, so I'm going to share the Desmos screen. All right, does everyone see the Desmos screen? Yeah? Yes, okay, cool. And I'm gonna go ahead into the wrench, where I can change my settings, okay? I'm going to change my x-axis to be negative 2 pi to 2 pi. I want to count by pi over 2, okay? So refresher on how we do that. I do not want to be in radians, or I don't want to be in degrees, but I want to be in radians. So we want to make sure the green is on the radian, okay? Now over here, I'm going to type in y equals cotangent theta. Okay, so with theta, you can literally type in theta and it will turn it into theta for you. So here's our graph of cotangent, okay? So they actually did it in red. Let's change it to blue to match our notes, okay? So that's one side of the equation. The other side of the equation said 1 over tangent. So I'm going to graph y equals 1 divided by tangent theta. Okay. And I'm going to change this one to be red to match our note. Okay. Let me turn the red one off for a moment so we can see. This is the blue, right? So this is our cotangent. This is our 1 over tangent. Okay, so cotangent, 1 over tangent. Cotangent, 1 over tangent. Same graph or different graph? Yes, right? They're the same. Cotangent, 1 over tangent. Cotangent, 1 over tangent, right? So I think what's so hard about trig is we get lost in like a lot of the algebra, okay? But thinking about this, when we think about verifying trig identities, what we're saying is, are these two sides the same? And we can see here that the blue graph and the red graph are the same graph, okay? So what that means, when we go back to the notes, we can write that they're the same graph. So that means that it's a true statement. We've verified it, okay? Now, let's go ahead and take a look at example 2, okay? So example 2, so we're gonna clear out these graphs. And the blue one, I'm gonna make, let's see, the left-hand side says tangent theta cosine theta, right? Tangent theta cosine theta. So in the blue one, I'm gonna write tangent theta cosine theta, okay? Okay. So this is the left-hand side of example number 2, right? Tangent theta times cosine theta gives us this picture. We should know what this picture is. What is this a picture of? This is a picture of sine, right? And if you look at example 2, isn't that what the right-hand side says? Sine theta. So let me type in sine theta here, and let's change this to be red, okay? So tangent theta cosine theta, sine theta. Tangent theta cosine theta, sine theta. Same graph, right? These two, the blue one and the red one, are exactly the same. They're not like kind of close. They're like literally right on top of each other. They're the same graph, okay? So if you look at the pictures and you get the same graph, then what that means is that the right-hand side and the left-hand side are equal. It means that whatever statement you have is true, okay? Let me stop sharing this for a moment. And we're gonna go back to the notes. Okay. So again, we're not going to draw the graphs out in our notes. You can if you want to, but all I did was just type in the left-hand side, type in the right-hand side, and I saw that they were the same graph. So that's our way of verifying the trig identity graphically, okay? It's actually a nice way. I know there are some of you out there who are always asking, like, what's like another way I can check my work just to make sure it's correct? This is a great way to check your work, right? If you get lost in the algebra, sometimes just knowing that the pictures are the same can help you sort of move forward, okay? All right. So that being said, what I really want to spend our time on today is verifying trig identities algebraically, okay? Like I said, unfortunately or fortunately, this is like one of my favorite things to do. It brings me a lot of joy because you can take these things that look like they shouldn't be equal at all and show someone mathematically that it is literally equal, okay? These all go back to the unit circle though. The unit circle was created from triangle, right? Layers, layers like an onion, make you cry too. All right, so let's take a look at example 2. All right, so we're looking at example 2 again. All right. So we have tangent theta cosine theta equals sine theta. So we just saw this question, and we saw that when we graphed it, we had the same graph on both sides. And so one of the things that we can also show is that these are actually equal using some algebra, okay? So I would go back to those 5.3 notes, and I would pull up the list of all the identities, all right? We're gonna continue to add to that list. I would encourage you to have it handy, just like you have your unit circle handy, okay? So another way that we can write tangent theta, all right? Look at your graphic organizer. What is another way I can write tangent theta? You're like leaps and bounds ahead of me. There you go. All right, so we can write tangent theta as sine theta over cosine theta. Now, what is the name of that identity? What is the name of that identity? Quotient identity, you got it. So here's why I'm writing these down, okay? On the answer keys, you'll see for the quiz, I do write down in blue like what identity I used, okay? Because I think it's really hard in the beginning. I've seen these kinds of questions so much that I can probably just figure most of them out without looking at the graphic organizer a ton. But I know that as folks who are just getting started with this kind of stuff, it's a little bit harder, okay? So that's why I put in like what identity we're using to help guide you along that list, okay? Now I really also like what Natalia said about cosine being cosine theta over 1. And sometimes I write things as fractions just so everything's a fraction to make my life easier, okay? All right, now here's one thing I'm going to be super picky about. You have to write the other side. So is someone accidentally unmuted?
That cream soda. That cream soda. Nasty.
If you are not muted, please mute yourself. Okay. All right. So this right-hand side, I want you to write it again. I know it's more writing, but think about how much writing I do that I don't have to do. Okay. So write out both sides of your identity. Okay. Now we get to the part where we cancel some things out. Sometimes things cancel, right? This cosine on the top and this cosine on the bottom cancel out. So if I were describing this step in an answer key, I might just write algebra to say like a general canceling of things out. But that makes the left-hand side equal sine theta, and the right-hand side is also sine theta. That's like saying 1 equals 1 or 5 equals 5. So now we've shown that those are true. Okay. Any questions about number 2?
Do we have to put the check mark?
No. I think I do because, again, these things bring me joy. So I'm like, they're the same. A plus Judy. You don't. Okay. So let's take a look at example 3. Okay. All right. So since we know that cosine and tangent is sine over 1, this can make our process faster. It can. Okay. But I want us to kind of think of these sort of as individual problems, so to speak. And I want us to practice using the graphic organizer that has all the identities on there for us, okay? So for example, another way of writing cosecant would be how? One over sine, yeah. So we're gonna have 1 over sine theta. Now, usually if it's already cosine or sine, I kind of leave it. So I'm gonna keep the cosine theta as cosine over 1, okay? And then I am gonna use the same quotient identity to write tangent, sine theta over cosine theta. And I'm gonna be mathematically precise and write the other side as well. Okay, so sometimes we need more than one identity in the same thing, but in this case, we used the quotient identity, whoops, for this one, and we use the reciprocal for the 1 over sine, okay? And now let's see if some things cancel out. Turns out this cosine and that cosine reduce, but also the sine on the top and the sine on the bottom reduce. So what's left? 1 equals 1. All right? And we could say that this is just algebra, okay? Yeah, and if you graph cosecant theta, cosine theta, tangent theta, okay? So if you have access to Desmos right now, if you pop this into Desmos, you're gonna get a flat line at 1. All three of those together, multiply, you're gonna get a flat line at 1. Yes, it reduces, and that's why you'll hear me say the word reduce a lot instead of cancel. It's not that it goes away, but it actually reduces to 1, exactly. Okay? All right, so a general guideline, because what makes this unit hard for folks is there's so many different tricks to try. I found that this little like how-to is helpful as a guideline, but as we do all these other examples, I will try and be really obvious about why we're making certain decisions. And I've picked these problems to highlight some of the strategies that come up a lot so that you might, oh, hi there. So you might have a bunch of strategies to try rather than a step like this is always going to work, but you'll have a bank of strategies to try. Okay, so given a trig identity, if we want to verify that it's true, what we're going to do is this. We're going to pick one side of the equation and we're going to work on that side. Okay, this is really important. I will be very picky about this. You cannot work on both sides at the same time. Okay, this is the Virgo. You must work on one side only. Okay, one side only. It's usually better to start with the more complicated side. And I know that it's complicated looks different to different people. So I'll try and make it clear like why I might start with a specific side. The second thing is you want to look for chances to factor or to square or to add fractions. And I'm actually going to add to this or break apart fraction. Okay. It's really important as you go. Don't just start working and even forget what you're trying to get it equal to. Please keep in mind which functions are in your final expression. Okay, so keep in mind what your end goal is, right? It's kind of like why we make you create an ed plan here at Mesa or at any school that you're at. You want to kind of map out where you're going. You don't want to just take classes just to take more classes. You want to make sure that they're getting you towards that transfer that you want to get, right? Why take classes that you don't need to take? Or how sad is it if you take the wrong class and you try to transfer and then you don't have the right class, right? So it's really important to keep in mind what your end goal is. Like if you're a bio major hoping to transfer to UCSD, you have to take Calc 2. Unfortunate, but true, right? So if you're like, I just didn't want to take Calc 2, then you're not going to get that transfer. On the flip side, if you are transferring bio to like SDSU, I don't think you need Calc 2. So you could take it if you want to, but it's not sort of in that end goal, okay? Now, our last sort of step here is try to convert everything into sine and cosine, okay? And that's one that we sort of already started to see and that I kind of tend to use a lot, is converting everything to sine and cosine, okay? So these are just some general guidelines, but we're going to walk through a few examples just to kind of practice. It's okay to feel like, wow, where is she making these decisions from? More than anything, I'm trying to highlight some of the most common strategies that we come across so that we're sort of collectively building a bank of strategies rather than like every question is going to be so different. If I tell you only how to do one question, it doesn't mean you'll be able to solve a different question, okay? So let's get started. Things just got real. All right, so we've got sine squared theta, secant squared theta plus sine squared theta cosecant squared theta equals secant squared theta, all right? Which one of these is the more complicated side? I think this one's a pretty easy one to say that one of these sides is a lot more complicated looking than the other, right? That left-hand side looks kind of like a beast. So we're going to start with the left-hand side and we're going to try and make it look like the right-hand side. Does that make sense? We're going to take that left-hand, I know, we're going to take that left-hand side, we're going to try and make it equal to the right-hand side, okay? So here we go. When I look at this, I see two different strategies, okay? So we'll walk through one and then we'll kind of walk through another. But just to kind of poll the audience a little bit, what are folks thinking here? What would people like to try? Converting things to sine and cosine, okay? Yeah, that's definitely one of the strategies that I was gonna try, okay? So let's go that way. So the sine squared is gonna stay, well, maybe put it over 1 because I'm gonna be working with some fractions, times, how do I write secant squared in terms of sine or cosine? Yeah, so we have 1 over cosine squared, okay? So far we've got reciprocal. All right, then plus sine squared theta over 1 times, how do I write cosecant squared theta as sine or cosine? Yeah, there you go. Not 1 over sine, but 1 over sine squared, okay? And so this is also the reciprocal. Virgo professor wants you to write the other side. Also, mathematics professors want you to write that other side, okay? All right. From here, once we've rewritten it, what can we do? We can reduce for sure, okay? So if we reduce here, we're gonna get a 1. And over here, we could do sine squared theta over cosine squared theta plus 1 equals secant squared theta, okay? So if we write in what we did some algebra, right? What can we do from here? I agree with that. I think it's very hard for people who don't love all the little details. Okay. All right, so sine squared over cosine squared sure does give us tangent squared. And all of these are on that graphic organizer from 5.3, okay? And there sure was, I'll let you look that rule up while I write this in, that we use the quotient identity here. Yep, good old Pythagoras says that tangent squared plus 1 equals secant squared. So you do have to write this last step. You got to replace that left side so that it looks exactly like the right side. And then you can give yourself a smiley face because that was hard work. Okay, let's just put here that we used the Pythagorean identity. Okay, so this is one way to think about this problem, right? We could say, let me turn everything into sine and cosine, see what cancels out and what I can use, okay? I'm not sure how different it is, but I could have said, looking at the left-hand side, that I noticed that sine squared theta is in both terms. And so maybe I would think about factoring out that term first. Okay, so like the sine squared is in both terms, so I just went ahead and factored that out, all right? And if I think about replacing things at this point, I might say this is 1 over cosine squared plus 1 over sine squared. Okay. Now, if I wanted to combine these two fractions, I can't add them the way they are, right? I cannot add 1 over cosine squared plus 1 over sine squared. How could I modify those two fractions so that I could add them together? Right, I got two fractions, I got to add them together. What do I need when I add fractions? Yeah, I need a common denominator, okay? So if I wanted to get a common denominator, I would take the first fraction, I'd multiply it by sine squared over sine squared, plus the second fraction, I'd multiply by cosine squared over cosine squared. Okay. Now do I have a common denominator? I do, right? So my inside fraction actually becomes sine squared theta plus cosine squared theta over sine squared theta times cosine squared theta. And we want to show that that's equal to secant squared, okay? What can I simplify from here? Look at that list of all the identities. Yeah, that sine squared plus cosine squared is 1. That's a fancy way of saying 1. So I really have sine squared theta over sine squared theta cosine squared theta. And we hope that gets to secant. Those two reduce. We're left with 1 over cosine squared equals secant squared. And then we can say that secant squared equals secant squared. Okay. I think the second way was a lot longer, all right? But what I think it highlights is the idea that there is more than one way to approach the problem, okay? Sometimes the two ways are fairly even in terms of amount of work or amount of writing, okay? And some of us see certain things better than others. And so we really want to use this as a chance to play to our strengths, all right? And I think these are the kinds of questions that the more we sort of talk them out with each other, that's probably a really good way to study. Brainstorm some ideas. What do we want to try? Just give it a go, okay? So 2 different ways to get to the same answer. All right, pick your poison. But in this one problem, we've shown basically all of the different strategies we could try for verifying an identity, okay? All right, let's move on. Let's take a look at example 5. All right, I'll give you a moment to take a look at that, and then maybe you folks tell me some ideas you have. Tell me what identities you might want to use and things like that. All right, so we've got one idea in the chat: convert tangent and secant to sine and cosine. For sure, why not? Okay. So if we convert a tangent to sine and cosine, we would get sine theta over cosine theta. And we could say that this is the quotient identity. And then instead of secant, we could write 1 over cosine, which is the reciprocal identity, okay? And we want to set that equal to sine theta, all right? Now, one added benefit to writing out that right-hand side or the other side that you're trying to match it with is you're reminding yourself what you're matching it with, right? It's not, you don't get lost in it, you know what you're matching it to. Now this, it looks like a lot because it's like a fraction in another fraction with another fraction, and it's got a lot of letters, right? There's really only one number here. And so my suggestion would be you could use the sandwich thinking, right? The bread pieces, you're going to smash those together to make the new numerator, and like the inside pieces, you're going to smash those together to make the new denominator. Or you could go back to that idea of multiplying by the reciprocal. So I'll leave that up to you, okay? But you could write this as sine theta over cosine theta times the reciprocal of the bottom. But you got to remember to flip that bottom, okay? And we hope that equals sine theta. And I think we can see here those two reduce. And we're left with sine theta equals sine theta. So much joy. The left-hand side looks like the right-hand side right now. Okay. All right, questions on number 5.
Yeah, on number 5, I just I mean the wording of this is probably wrong, but I thought of it as 1 over secant. So tangent times 1 over secant, which is tangent times cosine, and then that gives you sine.
So you almost like split it into 2 fractions in the beginning?
Yeah.
And then sine theta over cosine theta, and then this was cosine theta?
And I guess it's less complicated if I don't explain how I got there, but I was kind of thinking of 1 over secant with an amplitude of tangent would give me what? Because you're multiplying 1 over secant with tangent. And I was kind of thinking of how the tangent would be moving the 1 over secant around graphically. It's just algebraically going about this wasn't very easy for me before. So I'm going graphically.
Okay. So one thing to keep in mind, a function, so when we're multiplying functions, it doesn't work the same way as like the function in the front is the amplitude.
Yeah.
Okay.
I figured that as I put them one by one through Desmos, but that was like the train of thought behind why I got the tangents in front and then the other one.
No, I think that's totally a valid method. So sometimes even just sort of splitting the two, making more fractions means that they're side by side instead of on top of each other. And that is usually an easier way for us to kind of handle those multiple fractions. Okay, so I think that's actually a really good way of thinking about it as well. You get to the same thing because the cosines reduce and you just get sine equals sine. Okay. All right, let's take a look at example 6. All right, so I know that this is hard, and that's why we kind of want to get used to looking at that list of all the identities that we have, right? What is sort of jumping out of that list when we see something like sine squared theta times 1 plus cotangent theta squared theta equals 1? Like, which identities are jumping out at us? Like, let's use this one. All right, so 1 plus cotangent squared is cosecant squared, okay? So I know it's cumbersome to type, right? So let's just make sure when we're talking in person that we have that squared part there, okay? So we are going to start with that left-hand side, and we're gonna replace 1 plus cotangent squared with cosecant squared, okay? And we can make a note for ourselves that this is one of the Pythagorean identities, all right? Okay, what can we do from here? Our end goal is to make this equal to 1. So what can we do from here? Yeah, we could use the reciprocal identity. So we could think about that like, oh, what if we change everything to sine and cosine? We can see that cosecant squared turns into 1 over sine squared. Okay. And now I think it's a pretty straightforward reducing, and we're going to get 1 equals 1. Okay. All right. So some of them are going to be more complicated than others, right? So when we took a look at 4, we kind of started off with something that was a little bit more complicated. It had some more steps. 5 and 6, I think, were a little bit more straightforward, but that doesn't mean that the logic is easy for us to understand. It just means we really need to practice that idea of matching things to that list of identities that we already have, okay? So what we're going to do right now is we're going to take a short break, and then when we come back, we're going to take a look at the last few questions. And again, these are all highlighting different strategies that I know come up a lot, so I want us to kind of get practice with those, okay? So I'm going to stop sharing for a moment. All right, folks. Hope you were able to get a good stretch break in, maybe grab an extra snack or two. We are going to jump right back into the examples. And I did want to ask you folks, is it helpful to sort of just walk through these together? Or do you think this would be something you'd like to kind of try in some breakout rooms first? Like, where are we feeling on this? Helpful to watch. Okay. Breakout rooms sound nice too. Okay. So, okay. Maybe what let's do, we have 7, 8, 9, 10, 11. Okay. Maybe what we'll do is let's see, it's 12:04. We have about a half an hour left. Let's pop into some breakout rooms for 10 minutes, okay? And in your groups, pick a problem, work on it. All right, it doesn't matter which one. Pick one that seems like accessible. I think the most important thing is being able to talk through ideas like, I think we should try this identity, or I think we should try this identity. Okay. Now, I think some of us are a little bit more nervous than others about sort of putting our ideas out there, but I do think it's really valuable for us to practice, even if we're wrong, putting ideas out there. Okay. So let's go into some breakout rooms just for 10 minutes, and then we'll come back and we'll get through as many of these examples as we can, okay? Do remember, though, that we are looking to only work with one side of the equation, not with the other. We want to match it to the equation that we already have, okay? All right, folks, I know that wasn't a ton of time, but hopefully it gave you a little bit of time to at least talk through some strategies here. Is there any one question that folks were able to do completely? Kind of start off with a bright spot. No, nothing. No bright spots. All bad. Okay. All right. Well, we'll start with 7 then, and we'll kind of work our way through and see how far we get. Okay. All right. So in example number 7, I would say that both of these sides are probably equally complicated looking. So in this case, we're going to start with the right-hand side, and we're going to try to make the right-hand side look like the left-hand side. Okay. And so that means that for every step, I'm going to need to write that left-hand side down. And on the right-hand side, I'm going to start with this, but I'm going to introduce a newish trick, okay? So this trick is something that we learned in Math 116 in like a slightly different context, but what we're going to do is we're going to go ahead and multiply by 1 in a very fancy way. And the way I'm going to choose to say 1 here is secant theta plus 1. And if that's on the bottom, then it must also be on the top in order to say 1. Okay? So my reasoning here is multiply by 1. Okay? And now what I'm going to do is, since I have 2 fractions on the right-hand side, I'm going to go ahead and multiply straight across. And that's going to give me cosine theta plus 1 over tangent squared theta equals cosine theta times secant theta plus 1 over, and I'm going to multiply out the bottom, okay? So if I multiply that out, I should get secant squared theta plus secant theta minus secant theta, so those go away, and then minus 1, because negative 1 times 1 is negative 1. So all we did was FOIL the bottom, okay? Now you'll notice that I did not FOIL the top yet, and sometimes you have to and sometimes you don't have to, okay? So that's why I kind of sort of waited. We just did one thing in one step. Now for the next step, what I'm going to do is I'm going to go ahead and turn the secant right here into 1 over cosine. Okay, so let me say that one more time. I'm going to take the secant and I'm going to turn that into 1 over cosine. So I'm going to get cosine theta times 1 over cosine theta plus 1. And on the bottom, what I'm going to do is see if there's a way to use one of the Pythagorean identities to simplify this. Okay? So can someone find the Pythagorean identity that deals with secant squared? Right? What is that? What is that Pythagorean identity that has secant squared in it? Okay, just put that into the chat, whatever it is. Anyone?
Someone said in the chat, I don't know if you got the chats, but Gloria said 1 equals secant squared theta, I think.
I wonder where my chat window is. For some reason, it's not coming up.
Yeah, that's what I thought, because a few people brought it up, but I guess you didn't get them.
I did not. Thank you for your patience. I was like, this is very odd. I feel like there's something technically wrong because you all are generally not that quiet. Okay, there we go. Now I can see it. Thank you. All right, so let me catch up. Folks said tangent squared theta. Yeah, so tangent squared theta plus 1 equals secant squared theta. So I could say secant squared theta minus 1 if I subtract 1 from both sides. Tangent squared theta is another way of saying that secant squared theta exactly. Oh yeah, there we go. Okay, yes, exactly. This is the conjugates piece, right? So conjugates are super, super useful in so many ways. It could be with things like this. It could be with complex numbers, but they are definitely useful. So instead of writing secant squared theta minus 1, I'm going to replace it with tangent squared theta, okay? Which is nice because we are trying to make the denominator into tangent squared. So we've kind of already got that piece, right? And now let's see what happens with the top. Well, I could distribute. And let's see if that cosine theta plus 1 pops out on the top. Right? And we distribute here. Cosine theta times 1 over cosine theta is 1. Plus cosine theta times 1 is cosine theta. And we've got the top and the bottom equal to the other side. So we are good to go. Okay. So an extra trick to add to that bag of strategies that sometimes we can be creative on how we multiply by 1. Okay. All right, whoops. Let's take a look at 8, all right? Who thinks 8 looks like super, super gross? I think upon first look, it looks very intimidating, right? But yeah, but let's think about which one looks more complicated. Like, I think the left-hand side looks more complicated because it's got a fraction, okay? But check this out. This is also a throwback to things looking like we did factoring in Math116, which is that when we had a squared minus b squared, I think people knew that was a plus b times a minus b. But if we do a to the 4th minus b to the 4th, that actually equals a squared plus b squared times a squared minus b squared. Okay, now this was something that we took a look at in 116, all right? So when you learned how to factor in high school, this was probably, the first one was probably one that you learned and your teacher was like, you're gonna need to know this one. And the second one is just kind of like an extension of that, okay? And so it turns out that we can use this piece right here to help us with the numerator, secant to the 4th minus tangent to the 4th, okay? So if we apply this factoring to the numerator, I can turn secant to the 4th minus tangent to the 4th into secant squared plus tangent squared times secant squared minus tangent squared. Now that we can say we just factor, okay? So if you've been with me since August, you know I've said the factoring does not go away. If you are new to this class, the factoring does not go away. When we hit 150 in the spring, the factoring will not go away. Okay, so it's a good skill to invest in. Think about this as so many chances to get better at it, okay? And then the denominator, well, I don't know what to do with that, so let's just kind of keep it for now. Are we seeing what we need to do here to finish this problem off? What do we need to do to get these two sides equal? Yeah, all we need to do is reduce those, right? Wow. There we go. Okay. What rabbit hole did you go down?
I did a lot of weird factoring, and I just ended up with negative tangent squared theta on both sides.
Ah. You could also do some substituting for sure. But I think I wanted to highlight this one because any even powers you could factor the same way as that a squared minus b squared. Okay, so that's kind of a handy trick to know. All right, it looks like we got about 5 more minutes, and I think that someone had said that one of the groups did number 11. So maybe let's just jump over to number 11, maybe finish off on that one for today. Okay. So what do we think about this one? What did folks try for that one?
I think what we did first was we worked on the right side, and so we turned the secant to a 1 over cosine.
Mm-hmm.
And when you're dealing with fractions and like addition and subtraction, one of the things you want to do is you make the denominators the same. And so we would multiply the cosine theta over 1 with cosine theta over cosine theta. And that leads us to cosine theta squared over cosine.
Uh-huh.
And 1 minus cosine squared theta equals sine squared theta. And that is how we got them to equal each other.
I love it. Right, so you took your two fractions, put them together, and then did a Pythagorean substitution. Perfect.
Yay.
Yay. Okay, so common denominator, combine fractions, and a Pythagorean substitution gets us there, absolutely. Great. All right, so I'm sorry that some of us think all of these look gross. Don't take that personally. I know I enjoy these. I know not everybody does, okay? But I can tell you this, if you just kind of try and ignore these and like hope they go away, you're gonna be really, really sad about exam 3 because exam 3 is gonna be like a lot of these kinds of questions, okay? So it is a skill that we definitely want to build. It is a skill that like beyond 104, if you're looking to take 141 or 150, any of the pre-calc or the calculus classes, like the ability to think like this, not necessarily just like do things accurately, but the ability to reason through a problem like this is actually really valuable. Okay, and that's a hard skill to measure. So that's just kind of like, this is one of the ways we practice something called mathematical reasoning. Okay, so let's call it here for today. I'm going to stop sharing the window. I'm going to